In example 8.1, we are asked to determine if each ordered pair represents a solution of the given system. So let's look at the system. We have a first equation, 9x plus 7y equals 8, and we have a second equation, 8x minus 9y equals negative 69. So what you're going to find here in section 8 is that when we write our system out, we're not going to be using our function notation. And that can be a little inconvenient because when we do function notation, we can just call one equation f of x and the other one g of x, and it makes it really easy to talk about the different equations. Since we don't have function notation here, the best that we can do is come up with our own naming convention, and that's where the 1 and the 2 come from. So I can talk about equation 1 versus equation 2, for example. So let's start with equation 1. 9x plus 7y equals 8. And I want to see if the ordered pair negative 3, 5 is a solution for that equation. So I'm going to let x be equal to negative 3, y is going to be equal to 5, and then my equation is now going to read 9 times negative 3 plus 7 times 5 should equal 8. And we're going to check if we get a true statement. This will be negative 27 plus 35 is supposed to equal 8, and sure enough, we get the statement 8 equals 8. That's a true statement. All we have just shown is that this ordered pair is a solution for the first equation. It is not yet considered a solution of the whole system until we can show that this particular ordered pair also is a solution for the second equation. So that's what we're going to do next. For the second equation, we're going to take the same ordered pair and we're going to plug those in. X will be negative 3, y will need to be 5, and then we get 8 times negative 3 minus 9 times 5 is supposed to equal negative 69. That gives me negative 24 minus 45 is supposed to equal negative 69, and lucky us, we get another true statement. Negative 69 does equal negative 69. So at this point, we can now make our conclusion. Therefore, the ordered pair negative 3, 5 is a solution of the system. And we can't make this conclusion until we've proven that both equations are true because of this particular ordered pair. So that's part A. Part B is going to want us to test out a second ordered pair. Now, we had talked earlier in definition 8.1 about the possibility of there being maybe multiple solutions. So when we are asked to solve something, that means that we're supposed to find all of the solutions. Could be 1, could be none, could be 2, 3, 4, I mean, we don't know. And in this example, we're not being asked to solve, we're just being asked to check if the ordered pair are a solution. So since there's always a possibility that there could be multiple solutions, we could very well find another one that works. So I can't immediately say that, well, there's no way that another ordered pair is going to work, because it very well could. So let's go ahead and try it out. Number 1, 9x plus 7y equals 8, and we're going to let x be equal to 1, y will be equal to negative 2, and then 9 times 1 plus 7 times negative 2 is supposed to equal 8. That's going to be 9 plus negative 14 equal 8. This doesn't look good. Negative 5 equal to 8. That's a false statement. That's no good. So if I can conclude that the ordered pair is not going to work for one of the equations, then there's really no point in checking the other equation, because it's no longer going to be eligible as a solution of the entire system, because it has to work for both equations in order for it to be a solution of the whole system. So now we can make our conclusion. Therefore, 1, negative 2 is not a solution of the system. And that doesn't automatically mean that we can conclude that negative 3, 5 is the only solution out there. There could be a whole host of other ordered pair that could potentially work for us, but this is what we get if we only test negative 3, 5 and 1, negative 2.